I'm excited to share the new breakthrough on video quality assessment for real-time communications. So video quality assessment has received a lot of attention in last decade. It's played a very important role in control the quality for the video communication. There are two application scenarios. One is a professional video streaming. So you have the movie or TV drama content, and it's served from a wide range of audience. And so you have the high quality video as reference, and you can compare and measure the compressed video quality. And this is used daily in the streaming industry. The second scenario is either user generate content in different kind of platform, social media, or the conversational video. And these two kinds of video contents, you usually don't have the high quality video as a reference. So we have to do the quality assessment without any reference. That's called a blind quality assessment. For the professional video quality assessment with reference, my team at USC collaborated with Netflix on this project in 2014 and 15. We developed a new technology called VMAT, Video Multi-Method Assessment Fusion. And this now become de facto standard in the streaming industry. And the technology received the Technology and Engineering Emmy Award in 2020. And because of this success, then I received an invitation from Meta Engineer to work on the quality assessment for user-generated content and also conversational content. For this user-generated content or conversational video, there are three challenges. One, there's no reference available. Second, the computational resource at the user end, the edge or mobile devices, is very limited. Third, for many conversational video, you cannot have latency. So this low latency requirement also very stringent. And in order to achieve this kind of goals, overcome the challenge, you need a basically lightweight machine learning algorithm to do the quality assessment. And let me introduce myself. I'm William M. Hogg Professor at the University of Southern California. And I'm also director for the Multimedia Communication Lab. I've been with USC for more than 30 years. And I'm a fellow of the AS, IEEE, ACM, and so on. And I'm also an academician of Academia Sinica in Taiwan. In my lab at the USC for the last 30 years, we have broad collaborations with many companies. So here it shows just a brief list of the companies we have worked with. And I've collaborated with more than 70 companies throughout my 30 years at the USC. And this is the project with Meta last year. And so I would like to share our collaboration results. So we start from the blind image quality assessment. Later on, we move to the blind video quality assessment. And then we have the conclusion and report. First, I will talk about blind image quality assessment. So first, we need the data sets. And we not only need to acquire a wide range of the images with different quality, and also we need to get the user labels, so the user scores. And so in order to do the machine learning. And the current machine learning method, there are two categories, two methodologies. One is a more traditional one. You extract the features from images, and then you do the machine learning for that. And second is a deep learning neural net approach. So you basically do the end-to-end optimization, get the features, and then do the decision in one pipeline. and it's very usually hard to explain. And also another issue is the complexity of deep learning is huge and also require larger memory size. But in terms of performance, the deep learning solutions usually provide a better accurate prediction compared to the traditional method. So here we need to address two things. We want to have very lightweight algorithm, much simpler than deep learning solutions. And on the other hand, we still want to get a good performance, high prediction score, high correlation with the human score. So we are in the middle of the conventional deep learning. So we want to have the lightweight like conventional, but we want a good performance like deep learning. So it's a very challenging topic. So here I show the 4 images, and usually you ask the user to label each image with number 1 to 5. So from the worst to the best. And then one image you have multi-users to provide their scores, and then we do average for that score. So this average of multiple user score is called the mean opinion score for each image. So here I use 4 images to show the mean opinion score. So the left 2, it's a good images. And the third one, a deer, people like it a lot, the high score. And the right one, the tower, the light tower image, as everyone sees, its quality is poor, and so it's a low mean opinion score. Later on, I will show you the predicted score from our algorithm. So basically, our pipeline consists of 2 stages. The first stage is no supervision. We don't need the user labels. We just try to get the features from the image and automatically. So we don't use the handcraft features. We use some kind of a very powerful tool to find those features. And then we can select a subset of features more discriminant and more relevant to the regression purpose. And then the second part, we do the feature selection, use the supervision, and also we use the trained regressor to predict the score. And for the feature selection, we consider 2 stages. The first stage is a discrete cosine transform that's widely used in the compression. So we have a DC and we have AC coefficient for each local image block. So that gives you some kind of the feeling of the textures of a small window. And later on, we put the DC coefficient, we put all the DC together and go to the second level DCT transform. That gives you a more global feeling of the whole image. And then we also have the second stage, we have DC and AC coefficient. So these are all served as the candidates of the features. So this part shown in the left-hand side of the slide. The right-hand side slide, we try to check the discriminant power of each feature. So we basically have the feature from the minimum to maximum, and then we try partitioning in different locations between the minimum and maximum. And then each partition, we can find 2 half planes, left and right, and we use the mean of left and right as a prediction. And we can calculate the mean square error. And we add them together. And we want the mean square error as small as possible. So for each feature dimension, we choose a partition with the smallest mean square error. And that will be the loss function for that feature. And then we have many features as shown in the right bottom. We rank order them from the minimum mean square error from the lowest to the highest. And then we choose those features with a lower mean square error. Those are called discriminant features. So we select that and to do the regression. So this is a predicted result. For the left 2 images, we have very nice prediction. It's very close to the user mean opinion score. The right 2 are more challenging cases. The deer one, we underestimate because the algorithm see a lot of troll, in the background, it's blurred. So we feel maybe those are not high quality image. But actually, in this case, user really pay attention more to the deer rather than the background. So user like that. So somehow we couldn't take that into account yet. And the right one, we predict the low score, but not as low as the user mean opinion score. So these are very special cases, and we still need to fix it. And this slide shows the comparison of the different quality assessment methods, a blind quality assessment method. So the left one will show the different methods, and the middle two column is about we talk about two data sets. One is a life challenging data set. One is the Khan IQ 10K data set. And there are two major. One is called SROCC, one called PLCC. These talk about the predict score and the human score, the correlation. So 1.0 is the best, so they totally match. And less than 1, the higher the better. So then I want to point out the last two rows. So we can see the hyper IQA. That's the one. You see a bold faces. Bold means the best, okay, and underbar means second best. So hyper IQA has the best performance. So for all the cases, give the highest correlation coefficient. Our method, green BIQA, it's a little bit worse than that, but not much. So the gap is like around 0.05. But now let's move to the right part of the slide. So one is the model size. Model size, you can see the hyper IQA is 57 times more than ours. And then I want to show the flops, that's floating point operations, and for the whole image. And then the last column is a floating point operation per pixel. And then if you compare, you see the hyper IQA, the best performer, and then our method. You can see our complexity is 1, and then the hyper IQA complexity is 674. So this is almost like close to 3 order magnitude difference. So that shows even we sacrifice a little bit performance, but we are able to do for the real-time communication. Now we move to the blind video quality assessment. So here there are 4 video sequences, and basically the top 2 is sort of in the middle range, and then the lower left one is a very high score. The median opinion score is 4.0. It's a cat image in front of some kind of background, but cat has very high resolution, while the background is blurred. And the lower right is it's like a concert, but the resolution and the quality of the video is not good. Okay, so the pipeline, basically, in order to do the blind video quality assessment, we still build upon the foundation of blind image quality assessment for the still frame. But also we want to incorporate the temporal information. So we basically crop out some small cube, so including spatial and temporal 3D cube, and then extract the feature from this 3D cube so that we are able to get a rich set of features. And then we select the most relevant one using the same technique I introduced earlier, and then feed them to the regressor. So now this is the predicted result. The top 2, the predict score and the mean opinion score, very close. So that's good cases. And the lower left, the cat case, we underestimate the score because the background is blurred, so the quality from the background seems not good. But in this case, actually, humans pay attention to the cat. They really don't care about background, so that there is a gap between the human score and the machine score. And the lower right, the mean opinion score is much worse, even though we predict the low score, but not as low as the human labels. So this is an overestimated case. And again, I think this kind of video content is less available. So the machine learning cannot train this kind of video with high accuracy. Okay, so here I want to show the performance comparison between many methods. Again, the boldface means the best performer, and the underbar is the second one. So now you see I divide into two groups. The top group, basically all the deep learning method. The bottom two is our solution. And our solution, we also have two mode. One is a fast mode with a little bit worse performance. One is a normal mode with a better performance. And then you can compare the method by Li. For the two data set, their performance, 3 are the top, 1 is the second. And our green BBQA normal, 3 are second, 1 is the best. So basically, these two are competing technology. But now, in terms of performance, but now you see the model size and gigaflops. And you can see that in the memory size, the method by Li is 50 times of our method. And in terms of the computational complexity, is 715 times of our solution. So this high complexity and the high model size make them not attractive for the real-time communication purpose. So here I want to give a conclusion. So the takeaway is a video quality assessment for user-generated content and also the multi-party conversational video, still hot topic. And here we show a real workable solution for this kind of real-time communication purpose. And of course, the challenging is that there is no reference, so you can only rely on machine learning techniques. And you need a very effective feature extraction and also effective regressor. And we propose the green BIQA, green BBQA, and they can achieve the first tier performance in terms of the correlation with human experience. And its model size is much smaller. And compared to deep learning, they have the 50 times of our model size, and their complexity is 500 or even more times than our method. And in the future, there's still more work to do. I think one challenging is to have a small number of labeled data, but you want to predict a wide range of the visual content. So we look forward, continue to work with Meta in pushing this technology. So that concludes my talk. So I have several slides with references. So for interested people, you can take a look. Thanks for listening, and I look forward to your questions.